All right, everybody. Hello and happy Friday to all of you. We'll dive right in talking about non-covalent interactions. By the end of today, I hope to tell you why oil and water don't mix, and how soap works, and what trans fats are, and the difference between fats and oils. So we got a lot of ground to cover. We were talking about the non-covalent interactions, and you can group non-covalent interactions, as I said, are interactions between either charges or partial charges within molecules with those in other molecules. And so you've got ions, dipoles, quadrupoles, and then last time we were just barely talking about what are called induced dipoles. And this has to do with instantaneous, not permanent, transient, fluctuating electron density about a molecule. And it's not anything that persists. Of course, in this hydrocarbon, which is nonpolar, you expect there to be no net dipole, but temporarily there can be an induced dipole as the electron density shifts from one side of the molecule to the other. In particular, this happens as molecules approach each other. So for example, if I had two of these, as they approach each other, they would tend to polarize themselves such that the surfaces that were closest to each other were complementary in charge. And this, again, isn't a permanent thing. In the next instant, oops, now I forget which way everything was. In the next instant, you might expect this portion of the molecule to have a positive charge and this portion of the molecule to have a negative charge and so on. I forget whether blue or red is positive, but opposite, I guess, is for this discussion. And it can switch back and forth, but as they get close together, their electron clouds are responsive to each other and are correlated with each other so as to minimize the repulsion between the two. And this actually ends up being an attractive force. It's not very strong. Of course, the more actual charge you have, the stronger the interaction is. But I might call this sort of complementary electron correlation between molecules is another way to think of it. All right, so individually, any of these interactions are kind of weak, but if they, these induced dipole interactions are weak, but they can add up to be a lot. And for example, induced dipoles are how geckos can walk on walls and ceilings and stuff. All right, and we'll talk about the various factors that influence the strength of these interactions. So with, let's see. With ions, you might expect stronger interactions if there was more charge. You might also expect stronger interactions if the ions are closer to each other. Don't write this down, please, but Coulomb's law tells you that the strength of the interaction depends on the two charges and on the radius between the two. So ionic interactions get weaker as you move them farther apart. Dipole interactions are going to depend on the difference in electronegativity between the two atoms. The dipole will be stronger if there's a bigger difference. Same thing with quadrupoles, only if your electronegativity difference is bigger between carbon and hydrogen, you can have a more intense quadrupole. Incidentally, you might imagine, can you reverse the quadrupole? That sounds like I'm saying some kind of sci-fi techno-babble to fix the ship. We have to reverse the quadrupole. But of course, fluorine being more electronegative than carbon, if you do hexafluorobenzene, now the carbons are electron poor and the fluorines are electron rich. And you might predict, and it actually is true, that you could have a hexafluorobenzene ring sit down on top of a regular benzene ring, and their quadrupoles would align in complementary ways, and that actually does happen. Let's see. With induced dipoles, they can be stronger depending on a couple of factors. Let's see. I'm just going to shrink that. Strength here is going to depend on a couple of things. One is contact surface area between molecules. If molecules can really engage and get close to each other and there's a lot of overlap, a lot of surface area, the interaction can be quite strong. This is how the gecko works. Their hand and foot pads have, if you look at them at a microscopic level, have lots and lots of little fibers sticking out in all directions. The surface area is enormous, and it can actually make contact with the wall, and the induced dipole interactions are attractive enough to keep the gecko on the wall. Let's see, these are also sometimes called van der Waals, or probably you pronounce that Waals or something like that, I don't know. Interactions. And then you've got London dispersion forces, but on the other, and I don't know if that's named after a person or a place, but most people will call them van der Waals or dispersion or induced dipoles. I don't know. Okay, so you've got extent of charge, let's see, and then as I've said, all of these depend in strength on how close they are to the other dipole. There's a distance dependence, and it actually gets more intense the less charge you have. This is not important, but dipole interactions fall off quicker than ionic interactions, which fall off quicker than induced dipole interactions. So in terms of all the noncovalent interactions, it's a mix and match from this list. You can take a charge and a dipole, and you've got a charge-dipole interaction, you can call it that. For example, if you were to dissolve a sodium ion, let's see, we're using blue for positive charge. If you were to dissolve a sodium ion in water, the dipoles in water would tend to orient themselves so that the partial negative on oxygen was oriented towards the positive charge, and the partial positive on hydrogen was oriented away from the positive charge. And of course, I can't really do justice to this in 2 dimensions, but you can imagine a cage of water molecules sort of surrounding this ion. And this allows us to actually make an interesting comparison, because you've probably heard or been told that ion-ion interactions are really strong. And the evidence for that, you were told probably in Gen Chem that sodium chloride has an insanely high melting point. And I agree with you that if your reference state is 2 ions separated at infinite distance, then yeah, an ion pair can be strong. But sodium chloride dissolves easily in water, right? No big deal. And what's the explanation for that? Well, in the sodium chloride solid, you sort of have an infinite array of sodium and chloride ions stretching out to eternity, and you have ion interactions between sodium and the chloride that hold the salt together. The reason it can dissolve in water is because all of these ion dipole interactions completely compensate for the energy you lose when you get out of this interaction. So this is an important principle in organic chemistry and biology. you always, in order to determine whether something is favorable, you always have to compare, not to infinite distance necessarily, but you have to compare the two situations, in this case, the solid and then the dissolved state, and look at their relative energies. And so the reason sodium chloride dissolves is because the ion-dipole interactions can completely compensate for the ion-ion interactions you lose when you aren't dissolved anymore. It's actually more complicated than that. You will hate this, I'm sure, but you were taught in general chemistry that delta G equals delta H minus T delta S, which means that there are two ways things can be favorable. Okay, so somebody is going to ask me later today in my office, so how much of the equations from Gen Chem do we need to know for the test? Frankly, it's a boneheaded question to ask you on a multiple choice exam, which of the following is the equation for Gibbs free energy? Like, I have bigger fish to fry than that, folks. So please don't worry about that. The concept here is enthalpy represents interaction or bond strength. Since we're talking about non-covalent interactions, we'll deal with interaction strength. And entropy is related to disorder. Processes that are favorable have negative free energy. You can make a process favorable in two ways. First, the interactions you make can be stronger than the interactions you break, or the process can increase the disorder of the system, right? So in the case of solid sodium chloride dissolving, it's probably a little bit of both. Probably the ion-dipole interactions compensate for the ion-ion interactions you lose, maybe even more than compensate. So that could be a favorable entropy if the interactions you form are stronger than the interactions you lose. I haven't drawn the chloride ion. I should for completeness, but I don't want to, so I'll just put in parentheses solvated chloride ion. Solvated means surrounded by water molecules. And then how about disorder? Well, certainly disorder is greater from the crystalline lattice to floating around in solution and having much more freedom. So this is a favorable process, all right? Let's see. You maybe were taught that hydrogen bonding is its own thing. And I suppose that's true, though I prefer to think of it as just a dipole-dipole interaction. And it's actually broader than that, because you can have hydrogen bonding with anions and with quadrupoles too. I mean, the classic situation of hydrogen bonding is a water molecule interacting with another water molecule. And this is just, again, interaction of two dipoles, right? I agree with you that, for example, the dipole-dipole interaction in hydrogen bonding is stronger than, say, the dipole-dipole interaction in the following molecule. So this molecule is a ketone. Its name is acetone. It has a electron deficient carbon and an electron rich oxygen. And one of the things that keeps acetone as a liquid at room temperature is interactions between the individual ketone molecules as their dipoles align. But this dipole-dipole interaction is not as strong as the hydrogen bonding interaction here. And the reason for that is that hydrogen is smaller than, say, carbon or oxygen. So the hydrogen can actually approach this oxygen more closely, and the closer the interaction, the stronger the interaction. And so people separate out hydrogen bonding as its own thing because in many cases it's quite a bit stronger than your typical dipole-dipole interaction. There's a lot we could say about hydrogen bonding, but I think you sort of get the point. Questions there? Okay. So we could continue to mix and match these for like ever. I think last time I told you about the cation-pi interaction in which a positively charged ion interacts with the electron-rich face of the quadrupole of the benzene ring. That's actually really important in some neurotransmitter receptors. The acetylcholine receptor has an electron-rich aromatic group in its active site that binds the cation for acetylcholine. I mean, if you want to see it, you probably don't. I'm showing it anyway. This is acetylcholine, and that's the cation, the positively charged group, just sort of like in potassium. And it's going to also sit down on the face of an aromatic ring. In this case, as I said, you really don't want to know this, but the aromatic ring here is 1, 2, 3, 4, 5, is the indole ring from tryptophan. And it has the same sort of thing. It has an electron-rich face and an electron-poor edge, which I'll just indicate with the blue line there. And then I guess I should use blue for the cation on this positively charged ammonium group. And yeah, in the active site of the acetylcholine receptor, this nitrogen sits down on the top of that ring, and the positive charge holds it there. That's an important interaction. There have been a lot of scientists that have demonstrated that, and it's pretty cool. Non-covalent interactions are actually at the heart of all of the interesting things that happen in biology. Anything you want to say so far? Yeah.
I have a question about the benzene-potassium interaction. Would that be considered like an ionic bond?
Is that an ionic bond? No. In fact, there is no such thing as the ionic bond. Blasphemy. The reason I say that is because a lot of organic chemistry and biology happens in water. If all of organic chemistry and biology happened in space, then yeah, I would say the ionic bond is really strong. But in water, the ionic bond is readily replaced with ion-dipole interactions. So I don't think about ionic bonds anymore. I think of ion-ion interactions, and I compare their relative strength to other types of interactions. See what I'm saying? If you're in space, then yes, separating sodium and chloride to infinite distance is really hard because you can't replace the interaction with anything. If you're in water, no big deal. Is that sort of yes, no? Okay. All right. And this allows you now to understand, well, if the ionic bond is so dang strong, then how come it breaks in water, but covalent bonds don't? And now you sort of know the answer. Other questions? All right, so let's deal with oil and water, because this is a useful way of comparing the strength of various interactions. So here is a beaker. And it's going to be filled with some organic solvent. Let's, in this case, say like octane or something like that. So gasoline. Which last time I checked, gasoline was not actually orange, but what are we going to do? And then in this beaker we have, I'm going to copy and paste my way out of this. And then over here we've got good old water. Last time I checked, that was also not blue, except at depth for light scattering and stuff. Anyway, so you've got these two different substances, and if we mix them together, they refuse to mix together. Oops. So if you tried to mix them together, what you would end up with, and I think it depends on the relative density of gasoline versus water. I think in this case, well, that's interesting. Water's more dense. So you would have a layer of water on the bottom here, and then you'd have a layer of gasoline on the top, and lo and behold, they don't actually mix with each other. There's actually an interface between the two that you can see. So the question is why? Because if I took two different containers of water and they were different colors and I mixed them together, I mean, you've done this when you've been coloring Easter eggs and other things. You just get a blend of the two solutions. So what's going on here? And to do this, we have to do a couple of things. First, we need to consider the interactions between the molecules in gasoline with, I am sorry that the notifications of my computer are popping up. Maybe if you're lucky, you'll see a text from my son asking for something like more screen time or something like that. Okay, so this is a dumb aside. As parents of these teenage boys, we've tried to walk the line between like demanding compliance versus helping them make decisions and govern themselves, and our attitude has been to help them make decisions and then govern themselves. Nevertheless, we trust them only to a point, and so on their cell phones we have this app that lets us control the amount of time they have on a particular app, and they can always send a request for more, and it's really fun to press deny. Anyway, so if you're lucky, maybe you will see that. I think one of the biggest days in my oldest son's life was when he turned 18, and I deleted him from that app so that he had complete freedom. Hope he can now govern himself. I guess you guys can tell me how well that works, right? I don't know. You've been spending too much time on, I don't know, like me, on Wordle instead of doing important things. But it's intellectually stimulating. I'm really sorry. We need to get back on track. So, what's going on? We need to consider what's going on in gasoline, what's going on in water, and then what would have gone on if you were able to mix the two. We're going to think of an imaginary solution of the two, and we'll compare this situation with this one where they're separated in order to get a sense for why that happens, okay? So, gasoline is composed of various isomers of octane and some other organic molecules, 2, 4, 6, 8. We'll draw in some of the carbon-hydrogen bonds. Dang it, now I'm drawing in all of them. We want to show you the space that this molecule takes up, and sometimes the stick diagram doesn't really get that for you. So here is the electron cloud sort of surrounding this molecule. Okay, and in gasoline, the reason it is a liquid at room temperature is that as the molecules of octane approach each other, you get this instantaneous adjustment or polarization of their electron clouds such that they are complementary at the interface, okay? That's an induced dipole interaction, or alternatively, you can call it a van der Waals interaction, or if you want to, you can call it a London dispersion force. And it's not particularly strong. One of the reasons you know this is because you can evaporate gasoline more easily than you can water. So let's see, let's evaluate sort of the strength of this interaction in terms of enthalpy and entropy. In the gasoline just on its own, the enthalpy of the interaction is, well, you've got these weak van der Waals interactions. VDW means van der Waals, or induced dipole interactions. In terms of entropy, in the liquid, you've got a lot of disorder. Not as much disorder as you would have in the gas phase, but certainly way more disorder than you would have in a solid. The liquid molecules are sliding past each other, not staying in one place very long. But as they slide past each other, they are interacting via this weak van der Waals interaction. Questions you want to ask about that? Are there questions you should be asking about that? If it makes sense, great. Because this is sort of a geek out topic for me, sometimes I get caught up in myself, and it's hard to pay attention to what might not be making sense about what I'm saying. So don't be afraid to ask if something's not making sense. All right. In water, what's going on? Well, you have a network of water molecules. Let's see. And we'll call that hydrogen bonding. And this involves, making stuff up. This involves the hydrogen on one molecule, water molecule, interacting with the oxygen on another water molecule. And I'm going to try to illustrate something. I may regret it, but hopefully not. In water, the network of liquid water, the network of hydrogen bonding is very labile or malleable. It's very transient. It can change a lot. One water molecule is never hydrogen bonded to a specific other water molecule for any long length of time. You've got this transient network of hydrogen bonds. And I'm just showing a chain of water molecules that are close to each other, but it's going to be even more complicated than this. It turns out that it's actually not a huge stretch for a hydrogen bonding network to rearrange itself. I'm going to draw lone pairs on these oxygens. Actually, I'll draw them in a different color so you can tell the difference between the dotted lines for the interaction. Okay. It's actually not a huge stretch in an instant for this hydrogen bond here to become covalent as this oxygen steals that proton. Now, if you look at that, that's like, oh, I'm making H3O plus from OH minus, H3O plus and OH minus from two water molecules. You've talked about that in general chemistry. That's why water's pH is 7. But we're not talking about that here because in the same instant as we break that bond, this oxygen steals the proton from its neighbor. And in the same instant as we break that bond, this oxygen steals a proton from its neighbor, and so on. And so actually, it becomes difficult to tell which proton belongs to whom. So this is, again, dumb and may not be worth the time, but I'm trying to illustrate that. I'm going to erase all the bonds we broke. Okay, and I'm going to replace them with the new bonds here. Let's draw the new bonds in light blue. So we traded where the covalent bonds were and where the hydrogen bonds were. Do you see that? They just switched. They all traded their hydrogens off. And sometimes this is called flickering, but what it means is one hydrogen doesn't stay attached to one oxygen for very long at all in water. Yeah.
So what would happen if the hydrogens and the oxygens just stayed bonded to each other permanently? What would that mean for the...
So the problem with that, the question is, why can't we just have all of them bonded to all of the...
No. I'm saying, why can't the hydrogen just stay with the oxygen it was originally bonded to?
Well, it could. You would have hydronium there and then OH minus there.
But what if that didn't happen? What if oxygens just held onto their own hydrogens permanently?
I'm not sure I understand the question. If one oxygen were bonded to 3 hydrogens, it would have a positive formal charge.
When it's just pure H2O and it stays H2O and it doesn't take hydrogens from any of the water molecules around it, what would happen?
I'm struggling to answer that question because if you're going to allow for hydrogen bonding, it has to be able to happen. Okay, sorry, not a great answer. Yeah, go ahead.
So is there ever a period of time where the hydrogens just aren't bonded to the oxygen? Where it's like semi-bonds and the electrons are somewhat trading, but they're never fully bonded at that point?
Is there ever a time where a hydrogen isn't completely bonded to an oxygen? Not for very long. What you've just described is perhaps a transition state. So imagine a hydrogen being shared sort of evenly between 2 oxygens. That would be sort of a high energy transition state between the 2 extremes of being bonded here versus bonded there. But you're thinking right, because there's somewhat of a continuum. Now, there isn't any such thing in water as an isolated proton that's not surrounded by anything, because you've got water everywhere. But your question brings an interesting point. If I could take this water molecule, this solution of water, and drop a single extra proton in it, which oxygen has the proton? You put it, so to answer that question, we simply need to put that there, but you can see pretty quickly that it would be straightforward to change who had that extra proton. I'm not going to attempt to draw that. The idea is good enough at this point. But sometimes people think of H3O plus as not H3O plus, but rather as H2O 8 plus. Yikes, right? But that just reflects the fact that water is a really transient network of hydrogen bonds. So if we compare enthalpy and entropy of water to that of the gasoline, enthalpy, we've got stronger hydrogen bonds, stronger hydrogen bonding interactions. Entropy, we've got a lot of disorder. Again, because we're in the liquid state, we're not frozen, and as we've said, this is a lot of disorder because we don't even know which oxygens are attached to which hydrogens. They switch back and forth so quickly. All right? So with that in mind, we can now try to ask what would happen if we were to try to mix water and the hydrocarbon together in solution. All right, so let's copy the hydrocarbon. If you want them to be mixed together completely, that means that a hydrocarbon like octane here is going to be totally surrounded by water molecules. All right? And all the hydrocarbon has to offer are weak van der Waals interactions. And whereas in water by itself, the water has strong hydrogen bonding interactions. So it takes a hit in terms of interacting with neighboring partners if you're going to make water molecules be near the hydrocarbon, because the hydrocarbon simply can't replace the strength of the interaction that water's losing when it moves away from one water molecule to be close to the hydrocarbon. So what happens in response is that the water molecules in the immediate vicinity of the hydrocarbon I try not to anthropomorphize molecules, but they sort of start to panic, and they strengthen, they get closer to each other and stop moving quite as much so that they can strengthen their existing hydrogen bonds. They've given up some other hydrogen bonds because, of course, one water molecule can hydrogen bond with at least 4 other water molecules, right? You've got this one, and then you've got 2 lone pairs on the oxygen. 4 different hydrogen bonds per water molecule in regular water. But when you make those water molecules get close to the hydrocarbon, you don't have nearly as many hydrogen bonding opportunities. And so as a result, the water molecules close to the hydrocarbon arrange themselves in a somewhat rigid cage. Their movement is restricted because they're trying to compensate for their lost hydrogen bonds. Okay? And what you end up with is this somewhat rigid cage of water molecules around the hydrocarbon, if we were to be able to dissolve the hydrocarbon in water. So now let's think of this situation versus the 2 situations we just described over here. In terms of enthalpy, we have weaker dipole induced dipole interactions. I haven't displayed those there, but what we might say is it's true that the electron density of the hydrocarbon can try to adjust for the presence of a partial negative charge on oxygen, complementing it with a partial positive charge in the immediate vicinity. That's true, but those interactions are weak. Weaker than the hydrogen bonding interactions that we lost. And then the other thing is entropy. What do you think that comparison is? At least for these water molecules in the immediate vicinity of the hydrocarbon, what's their entropy like or disorder like relative to the way it was when they were just on their own? Should be lower, right? Entropy is lower, disorder is lower, they are not moving as quickly. Remember, entropy or disorder is related to how many ways a system can be, and if molecules aren't moving very fast, there's fewer ways it can be. There's less disorder. So you've got this rigid ice-like cage of molecules, water surrounding the hydrocarbon, and so we're going to say lower entropy. Okay? And what this means, if we were to make this solution and we got weaker dipole-induced dipole interactions, the enthalpy is going to be unfavorable. The enthalpy change for dissolving would be unfavorable. And the entropy change would also be unfavorable. Okay, now go back to what I told you about things that happen easily or readily or spontaneously. Delta G equals delta H minus delta T delta S. If entropy change is unfavorable and enthalpy change is unfavorable, then free energy also has to be unfavorable. And therefore, the equilibrium constant for dissolving is really, really, really low. It doesn't happen because it's just not favorable. It's not downhill in energy. All right, questions about that? Why am I spending so much time talking about oil and water? Well, this is the basis of something called the hydrophobic effect. And the hydrophobic effect, hydro meaning water, phobic meaning afraid. Oil doesn't like to interact with water. Oil or hydrocarbons are hydrophobic. Not because they are scared of water, and also not because the interactions between the two nonpolar molecules are so strong, because they're not. But it's because if you dissolve the nonpolar molecule in water, that doesn't lead to a decrease in free energy. You lose interaction strength and you increase order, you lower entropy, and both of those things are unfavorable. Yeah?
What does it mean when you, like, isn't enthalpy like a number? Like, why is it enthalpy
Sure.
weaker dipoles?
Right. We could put a number on the strength of this interaction. Interactions are favorable, negative numbers. We could put a number on the strength of these interactions and a number on the strength of these interactions. And what I'm saying is if you take the interactions you gain, you subtract the interactions you lost, that number is going to be positive, meaning unfavorable.
So does the enthalpy, so when you say the enthalpy of weak interactions, does that mean it's lower? Enthalpy is lower?
Enthalpy like free energy, if it's better, it's more negative. So you have to be careful with lower versus higher.
Okay, so
What I'm saying is delta H would be positive for this. Suppose the strength of this interaction is minus 100, the strength of this interaction is minus 100, the strength of this interaction is minus 50. Minus 50 minus 100 minus 100 is plus 150. So that's unfavorable. And in general, I mean, if you don't like doing the math, if the interactions you form are weaker than the interactions you broke, it's unfavorable.
so it's those the bonds over there are so weak that are much weaker than the bonds off of that.
Right. Well, yes. The big change you have is these interactions weren't very strong to begin with. The big change is you've lost hydrogen bonding opportunities. Yeah. Okay. So it's possible to misunderstand this. Some people talk about the strength of hydrophobic interactions. It's all about water entropy, and it's all about loss of hydrogen bonding. A couple of application principles of this. Most of the molecules or enzymes or workhorses of biology are proteins. These are polymers of amino acids. Some of the amino acids have polar groups on them, like hydroxyl groups or groups with charges. Others have nonpolar groups, like what I'm drawing here, even a benzene ring. And what happens if in water is that the nonpolar, because of what I've just described, because water around these nonpolar groups would be in this ordered ice-like cage, because of that, it's actually favorable for the protein to twist back on itself and fold such that the nonpolar groups are on the inside where they are not exposed to water. Whoa. That's, yeah, terrible. Let's try that again. So this is the phenomenon behind a lot of protein folding that you may learn about in biology or biochemistry, that the protein chain will fold back on itself to form an interesting shape, but the driving force is that we want to minimize the exposure of nonpolar side chains to water. Okay, now the concept of van der Waals interactions is important for soap, and it's important for understanding lipid bilayers and oils. So let me give you an interesting situation. Let's see. Why not? So this is a molecule that is could be a component of soap. Okay? You have a group here at the top of the molecule that's polar and has a negative charge, so we'll color that red, except we need a bigger font. There we go. And then you have this nonpolar tail that is not capable of hydrogen bonding interactions. So I'm just going to highlight that in gray. Oops, I wanted this. And you can imagine that if I put this in water, you'd have a similar problem to what we just described. The polar group could interact with water just fine. The nonpolar tail, if it were completely exposed to water, that's going to result in this entropy loss situation that we just talked about, where an ice-like cage of water molecules surrounds the nonpolar tail. So what happens is that these molecules self-associate. Man, this is going to take too long. I really also like it, so. All right, they self-associate with each other. You're getting the idea here. Orienting the polar groups towards water and the non-polar tails towards the inside, circling the wagons, so to speak. And you end up with this, what's called supramolecular structure. It's a structure of multiple molecules. And it's called a micelle. Out here is the water. We'll just draw that in blue. Out here is the water.
Does it make a sphere?
Yeah, makes a sphere. And the reason it makes a sphere is really because of the conical shape of that molecule. Notice that the polar head group is here, and then we kind of shrink down to that size at the end. And so if you think of stacking a lot of these cones together, it forms a spherical micelle, and in the interior, that's where you've got dirt and grease, and on the exterior, it's soluble in water, so it just washes away. So this is how soap works. Okay? Now, I want you to think, I'm going to draw something, and I want you to think about how the situation would change if we made a very similar molecule with a slightly different shape. So what I'm going to draw you now is phosphatidylcholine. It's got a phosphorus group here. It's got a positive charge here, negative charge there. Let's see. And then here, it's got two long-chain carboxylic acids. And I want you to think about the difference in shape between what we've just drawn here versus the molecule of soap, which is sometimes called a surfactant. This is a surfactant up top. This is a lipid below. And I want you to think about the consequences of shape for this molecule versus that one. We'll need a couple more minutes next time on this subject. We'll move on to chapter 4. We're not going to get all of chapter 4 done for the exam. What we don't get to will be on the next one. Have a good weekend.